only. Sorry. Okay, yeah, it's my pleasure to introduce Professor Min Dong from the Academy, Chinese Academy of Science. He's actually currently visiting at Melbourne, but unfortunately, face-to-face seminar had been cancelled due to the storm. But at least we can deliver this remote seminar, so it's great. Professor Dong commenced his research career at the Tianjin University in 2008 and served as a faculty member until 2021 when he moved to CAS. He also served as a visiting researcher and Marie Curie Fellow at the Imperial College London. At Imperial, he collaborated extensively with Professor Jason Wu, and he produced many interesting papers about high Reynolds number asymptotic nature of boundary layer instabilities. More recently, Professor Dong has expanded his research to more difficult and challenging area like complicated surface effects to instability or some non-Newtonian hypersonic effects to the boundary layer instability. The title of his talk today is Principle of the Fundamental Resonance in Hypersonic Boundary Layers and Low-Order Dynamical Model. So the mic is yours, me.
Okay, thank you. Thanks, Tango. This work is jointly done by me and Ren Jie-sung, who is my postdoc in Chinese Academy of Sciences. And also the collaborator is includes Lei Zhao from Tianjin University. So my talk is about hypersonic boundary layer transition. And let me first introduce the background of this topic. So for boundary layer flows, there could be two different transition scenarios depending on the free stream, the levels of the free stream turbulence. If the free stream turbulence are low in intensity, the transition will follow a natural route, which is also called the supercritical transition because we can see the exponential growth of the linear instability. And the scenario will have four different processes. First one is the receptivity, which means the background perturbation will enter the boundary layer and generate the instability modes. Then we can see a long distance growth of the instability modes. When they arrive at some finite value, they will interact with each other and distort the mean flow. Then we can see the breakdown of the laminar flow and the emergence of turbulence. If the free stream perturbations are high in intensity, we can see a completely different scenario. The exponential growth of the linear instability mode will not be observed. And we call this the bypass transition of the subcritical transition. At the beginning, we can see snapshot is shown here. We can see at the beginning, there are some longitudinal streaks here. They are forced by the free stream high level turbulence. Then the streak can grow transiently. When they saturate, they will support the secondary instability, for which the small scale perturbations will appear and grow. Then we can see some turbulent spots. And eventually the turbulent spots will merge and propagate to the downstream location, and we can see the fully developed turbulence. In this talk, I will focus on the natural transition route, and particularly on the nonlinear breakdown process. So there are three different kinds of nonlinear mechanisms for this process, including the fundamental resonance, the subharmonic resonance, and the oblique breakdown. They appear in different parameter spaces. When the dominant perturbation in the early stage of the linear process is the 2D mode. This axle is the frequency, and this is the span-wise wave number. If the 2D mode appears, then we can see that the span-wise wave number is 0. If the 2BD mode is dominant, they will not cause transition directly, because and they will support the exponential growth of oblique modes. If the most unstable oblique modes have the same frequency as the 2D mode, then we can see some pattern like this, which is called the fundamental resonance. If the oblique modes has a frequency being a half of the fundamental mode, then we call it the subharmonic resonance, and the pattern is like this. They are quite different. And if the dominant modes in the early stage of the linear phase are 3D, then we can see the oblique breakdown scenario, and we can see the lambda pattern like here. The parameter spaces are summarized here. So we for the fundamental resonance, we have the 2D fundamental mode with frequency omega, and a pair of 3D oblique modes with the same frequency omega. And for subharmonic resonance, we have dominant 2D mode and the 3D oblique modes with frequency a half of the fundamental mode. Then for the oblique breakdown, the dominant perturbations are a pair of oblique modes like this. Okay, so particularly for hypersonic flow, if we do some secondary instability analysis, we can see the fundamental resonance is more likely to be observed. And the transition process can be summarized like this. The linear receptivity stage, the linear instability stage, for which the 2D Mach mode, the Mach mode is the instability mode in the hypersonic flow. The 2D Mach mode is the dominant one. Then at the end of the linear region and at the beginning of the linear region, we can see the 2D Mach mode will support the exponential growth of the oblique modes with the same frequency. And we call it the fundamental resonance, FR. Then we can see the transition to turbulence. These are some simulation results from Fussel's group. We can see at the beginning the pattern is a planar wave, and in the linear phase we can see the 3D pattern, and eventually we can see the turbulence. If we do some time average, the traveling wave will be removed. But we can see some longitudinal streaks just located in the linear region, and the longitudinal streaks not only appear for the streamwise velocity, but also appear for the temperature. Then we want to do something more. We want to introduce some key phenomena appearing for the fundamental resonance process. So as I said before, in the linear region, we can see some longitudinal streaks here and here, and this is a simulation. These are from experiments, and we can see at this region there is a hot spot, and here in the downstream region there is another hot spot. And in between, it seems the temperature is lower. This can be revealed, shown by observing the CF curve and the wall flux, heat flux. CF curve means the friction at the wall, and we can see there are overall two peaks here and here. The first peak is induced by the separation of the 2D fundamental mode, but it doesn't cause transition directly. The friction and the heat transfer will be reduced in the downstream region, but the 2D mode will support the growth of the 3D modes, and this will cause the emergence of small-scale structures. They can produce sufficient Reynolds stress. Then they will distort the mean flow again and cause the transition eventually. So there are two different steps related to different mechanisms. And the question is, why the streak here appear, and if it is important in the fundamental resonance process. This has not been revealed before, and recently we have done some asymptotic work to describe this. Before doing the asymptotic analysis, we want to do some numerical calculations based on some simplified method. The numerical setup is just a flat plate inserting into a hypersonic flow, and there will be a shock. But for thin plate configuration, the shock is very weak, and between the shock and the surface, we have a viscous boundary layer, and the boundary layer will grow slowly in the laminar phase, but it will grow faster in the turbulent phase. What we want to do is to calculate the evolution of perturbations, particularly for the linear phase. And we choose a computational domain and start from a position in the laminar region. We introduce a number of instability modes at the beginning, and we want to see their interaction in the late phase. We choose the Mach number to be close to 6, and the reference length is the characteristic boundary layer thickness. We introduce the Reynolds number to be 2000, and the wall temperature is about 7, which is close to the adiabatic wall for a perfect gas flow. And at this location, we can introduce the parallel flow assumption and calculate the awesome field equation to obtain the instability modes. And this is just a demonstration of the instability property. So we expand the perturbation in terms of a waveform, and we want to see the spatial growth. So we let the frequency omega to be real, and the alpha, the streamwise wave number, to be complex. And the opposite of alpha I represents the growth rate. Overall, we have two peaks as revealed by Mach. The first peak is very mild, but the second peak is very strong. According to Mach's paper, the two different modes are referred to as the first mode and the second mode respectively. And the second mode corresponds to a higher frequency, and this one is more unstable, apparently. And at the beginning, at the entrance of the computational domain, we introduce 3 Mach modes. The first one is has an amplitude of 2.5 times 10 to minus 3, and the frequency is 0.11. It's just here, around the second mode frequency bound, and the span-wise wave number is 0, which means this is a planar wave. And we also introduce a pair of small oblique modes with the same frequency but opposite span-wise wave numbers, and the amplitudes are much lower than the dominant perturbation. Then we use a parabolized stability equation to calculate the evolution of the perturbations. This is a well-established method to calculate the flow, the perturbation evolution in the laminar phase, but it will blow up when the turbulent is reached. And here we show the CF curve. CF curve means the friction at the wall. It also relates to the shear, the velocity shear of at the wall. Okay, so we can see there are overall two sharp increases. The first one corresponds to the saturation of the 2D mode, and the second one corresponds to the secondary instability of the streaks, which is induced by the fundamental resonance. And we can also show the perturbation field. This is a top view. This is these four are top views. This is the front view. For the top view, we show the instantaneous velocity at two different normal locations. And we can see at the beginning, they are planar. And at the end of this simulation, we can see the 3D pattern. And we also do the time averaging, and we can see the longitudinal streaks here. And also, if we see the front view, we can see the vertex. And the vertex will interact with waves, like the wave interact vertex wave interaction. But at this stage, it is not the same as the self-sustaining process in the turbulent flow. We have to consider the role played by the 2D fundamental mode. Then we can summarize the numerical results by introducing the evolution of the Fourier modes. So here, the red one means the evolution of the 2D fundamental mode here, and the blue one is the oblique mode introduced at the beginning. But oh no, this one, sorry. The black one is the oblique modes introduced at the beginning, and the blue one is the mean flow distortion. Okay. So at the beginning, every mode evolve according to the linear regime. So here, as compared with the dots here, but when x is arrived to a sufficient downstream location, the oblique mode will grow very fast, much faster than the linear prediction. And at the same time, we can see the sharp growth of the streak mode, which has a zero streamwise wave number, and also the high order harmonics. The streak mode at this stage is dominant, and it eventually will overwhelm the amplitude of the fundamental mode and become the most important perturbation in this stage. If we summarize the growth by plotting the growth rate, which is the derivative of the amplitude with respect to x, we can see these three perturbations are of the same growth rate at this region, and it seems that they are phase-locked, and we call this the fundamental resonance regime. And our question is why the streak mode at this stage is dominant, and why we need to consider if the streak mode in this region is very important to trigger the boundary layer transition. That's the question we want to answer. Then we want to do some asymptotic analysis based on these observations. So first, we want to show some key scaling relations. So we introduce sigma as the common growth rate of the secondary instability modes. which is like this. Is this okay? Since they grow with the same growth rate, the sigma should be introduced here as an independent parameter. And for the fundamental mode, we call it 1, 0. There are two numbers. The first one is the frequency, and the second one is the span-wise wave number. So for the fundamental mode, the wave number is order 1. It is comparable. The wavelength is comparable with the boundary layer thickness. But the growth rate for the fundamental mode here, we can see it seems to be saturated, and this minus alpha I tends to be 0, which is much smaller. And the growth rate of these modes, the secondary instability modes, are much larger than minus alpha I, but it is still smaller than order 1. And for the streak mode, which has a 0 streamwise wave number, but a finite span-wise wave number, the streamwise wave number is 0, but the streamwise growth rate is about sigma. And also, for the oblique mode, we use we use 1 plus 1 or minus 1 to be a pair of the oblique modes, and the wave number in the streamwise direction has the same value, same magnitude as the fundamental mode, and it is also order 1. And the growth rate should be comparable with the sigma, the growth rate of the streak mode. And for the high order harmonics, which are passive, and we do not need to consider it at this stage. Then we want to see the key amplitude scaling. So for the oblique mode, OM is the oblique mode. The amplitude should be much smaller than the streak mode, which was revealed by this figure. So this is the oblique mode. This is the streak mode. The amplitude is much smaller here. And the streak mode is smaller than the fundamental mode. Here, streak mode at this stage is much smaller than the fundamental mode. And what we have found is that the fundamental mode, dimensionless fundamental mode amplitude should be comparable with the dimensionless growth rate of the secondary instability modes. So they are comparable. And the amplitude of the oblique modes should be forced by the nonlinear interaction of the fundamental mode and the streak mode. Then we have this equation. For the streak mode, it shows that for the V and W, there are some streamwise verticities, and we call it the rows. And for the streamwise velocity, we call it the streak. And the rows, the amplitude of the rows are much smaller than the streak, the amplitude of the streak. And they have this kind of relation. And then we can construct a triad resonance system. For the fundamental mode, it is governed by a linear equation. But for the oblique mode, it is forced by the interaction of the fundamental mode and the streak mode, because we have said this at the beginning. And then for the streak mode, the streamwise velocity is driven by the linear regime, because on the right-hand side, it is 0. But for the V and W, it will be driven by the linear interaction of the fundamental mode and the oblique mode. But the question is why the streak grows. This is because the lift up mechanism, because we have the rows. The row will induce the streak flow due to the lift up mechanism. Then we can summarize the scenario in this sketch. So here, this sketch is different from Wolff's self-sustaining process, because we have the role of the fundamental mode here. So the fundamental mode can interact with the streak mode and generate the 3D traveling mode, the oblique modes. Then the oblique modes will interact with the 2D fundamental mode and generate the row structure. Then the row structure will drive the growth of the streaks due to the lift-up mechanism. And if we want to write down the equations, we need to revolve the asymptotic structures for these different modes. For the fundamental modes, fundamental mode, we have a double deck structure, the main layer and the Stokes layer, which is caused by the viscosity. And for the streak mode, we also have 2 layers, but the wall layer is much thicker than the Stokes layer. And for the oblique modes, it should be described by a 3-layered structure, like here. Then, in the main layer, we can construct the triad resonance mechanism. So we have to first expand the perturbation field in terms of a series of perturbations. This is the mean flow distortion, and 1, 0 means the fundamental mode. 1, 1 means the oblique mode. 1, -1 is another oblique mode, and 0, 1 this is the streak mode. The key scaling relation is epsilon 1 0, 1 0 is much greater than epsilon 1 1, and epsilon 1 0 is much greater than epsilon 0 1. And the key relation is epsilon 1 1 equals to epsilon 1 0 times epsilon 0 1. And the growth rate sigma, the common growth rate sigma, is comparable with epsilon 1 0. By doing this, we can introduce the triad resonance system. For the fundamental mode, we expand the perturbation in terms of epsilon 510 hat times e to an exponential traveling wave form. And this mode in the main layer is governed by the Rayleigh equation. But for the streak mode and oblique mode, the interaction appears here and here. They are coupled. Then we arrive at a coupled linear equation. So we need to first solve this equation to obtain the perturbation profiles of the fundamental mode. Then we use these profiles in this coupled system and obtain the growth rate, the common growth rate. Okay, so that's in the main layer. What about the wall layer? Because we observe that when y tends to 0, tends to the wall, we can see some singularity. V is okay, but U and T is temperature, U is streamline velocity. They will grow like log y, which is very large as y tends to 0. And we need to consider the viscous wall layer. By doing some mathematical expansion, we can see for the wave for the streak mode, the leading order term is log epsilon, and for the oblique modes, the leading order term is log epsilon. Only U is log epsilon. W is order 1, so they are different. And if we do some detailed calculation, we can obtain the inhomogeneous forcing from the wall to the main layer. And we got the V01, which is the inhomogeneous forcing for the streak mode. And this is the inhomogeneous forcing for the oblique modes. And we got these values, and we can update the boundary equations for the main layer and obtain an improved asymptotic theory. Okay, then I can show some numerical results for the predictions. So if we do not consider the wall layer, we can predict the common growth rate like this curve as a function of Reynolds number, and the black one is obtained by NPSE, which is numerical, and we can see this is a standard benchmark. And if we improve the boundary condition by considering the wall layer impact, then the agreement is much better. But we still have a small error here, which is because in our system there are two small parameters. One is Reynolds number to -1, and the other is epsilon 10, which is the amplitude of the fundamental mode. Then we fix the Reynolds number and change epsilon 10, and we can see the agreement between the NPSE and the asymptotic predictions are very well. We also show the comparison of the eigenprofiles for the streak mode and the optic mode in the main layer. But right now in the wall layer, we didn't consider it because we need to consider to expand the perturbations into the second order. Then we have so far we have obtained the intrinsic mechanism of the fundamental resonance. We want to construct a low-order model to show the interaction between the fundamental mode and the other modes. If we want to do this, we want to start from some existent model, which is the self-sustaining process. This was given by Wolff in 1997, and we have in this model there are four different elements: the mean flow, the streak, the row, and the wave. And their interactions can be summarized in this sketch. The streak will support the secondary stability modes, for which we can see the exponential growth. Or we can see the growth of the wave, and the wave can produce some Reynolds stress to generate the stream vortices. Then the stream vortices will generate the streak by the lift-up mechanism, and many terms are related to these the interactions. But however, this is for a kind of equilibrium state, and if we want to show the supercritical transition, this system is not sufficient. Then we want to do something more. We introduce the fundamental mode, and we want to see their interaction in a new model. And in this model, we still use the mean flow, the streak, the row, and the wave. But additionally, we will introduce F as the fundamental mode here. And this sketch is more complicated than this one, the self-sustaining process. And here we want to emphasize the role of the fundamental mode here. And the terms under the underlying terms are the additional terms in our model. And if we every term has a particular meaning. For example, in this one, this term is the mean flow distortion caused by the fundamental mode, and this is the fundamental mode interact with the wave structure and cause the growth of the row. And for this is the linear growth of the fundamental mode, and these are the correction of the other modes to the fundamental mode. And also and all the terms with R to -1 is the viscosity. Okay, so this system is a fifth dimension, and we want to see the results. if it can show some more transition scenarios. Then we show the phase diagram starting from some small perturbations. Actually, we want to emphasize from this system, we have two families of solutions. And here we want to show one family of solution by plotting the amplitude of the fundamental mode as a function of the Reynolds number. There is another family of solutions which is related to the self-sustaining process. And for this that solution, F is 0. And here, starting from a small Reynolds number, we can see the laminar flow is for which F is 0 is a stable solution, fixed point solution. And as the Reynolds number increases to a certain value, we can see the linear growth of the fundamental mode, which is attributed to the linear instability mechanism. The linear mode will be saturated in this region, and it will support the fundamental resonance when the Reynolds number is further increased here. So we can see here. And if we see the phase diagram, we can see from the laminar stage, it will go to this equilibrium solution. But because of the growth of the secondary instability mode, including the streak and the wave, it will eventually shift to this fixed point. And if the Reynolds number goes further, becomes larger, the equilibrium state will become a kind of periodic orbit, and then we can see the periodic doubling bifurcation from P1, P2, P4, and eventually we can see the chaotic behavior. And further increase of the Reynolds number, we can see there are two different attractors, and we can and there is a boundary crisis here, and after beyond that Reynolds number, we can see eventually the self-sustained process will be arrived. This is the upper branch of the second family of our solution. So as the Reynolds number increases, we can see the scenario from laminar to equilibrium one, the saturation process, and the fundamental resonance process. Then we can see the period doubling bifurcation. Then we can see the chaos, and eventually we can see the self-sustaining process for the turbulent flow, the wall turbulence. And also we want to emphasize that since the system has two different attractors, we can starting from different perturbations, the final state will be different. This is for a relatively small Reynolds number, and starting from a relatively large perturbation, we can see eventually go to the self-sustaining process. And if the perturbations, the initial perturbation is relatively small, the laminar flow will be eventually arrived. Okay, but if Reynolds number is relatively large, starting from a larger initial perturbation will also direct to the self-sustaining process. But if it is smaller, we can see eventually the fundamental resonance here. So these are subcritical transition route. These are the supercritical transition routes. And for boundary layer flows, there is another thing we need to consider, which is the non-parallelism, for which as x goes to downstream, the local Reynolds number should be increased as well. So in this plot, we want to show this the impact of the non-parallelism for the evolution of the perturbations. So here, because real number is proportional to square root of x, then we change our real number gradually. And at the beginning, it is a laminar case, and the fundamental resonance is not observed. And when the real number is larger than a certain value, we can see the exponential growth of the fundamental resonance mode, and the strict mode is also the dominant one. Then we can see that we can arrive at the equilibrium state. Then we can see the period doubling bifurcation stage, and eventually we arrive at the chaos flow. And when the boundary crises appear, we will eventually arrive at the self-sustaining process. Okay, I think it's time to summarize here. So I have shown the principle of fundamental resonance, which is actually a triad resonance among the fundamental mode, the strict mode, and the oblique modes. And also we have introduced an asymptotic model for the growth and for the growth and the perturbation profiles of the fundamental resonance. The asymptotic predictions are confirmed by the NPSE calculations. And at the last, I introduced a low-order dynamical system, which can demonstrate both the supercritical and subcritical transition rules. Okay, thank you. I think I can stop here. Thank you very much.
Thank you, Ming, for a very interesting talk. So if there's any question, maybe just unmute yourself or put your comment in the chat box. Or maybe I can start. So let me first try to understand your, some flow of your talk. So you started from analysis. So you started your analysis from Navier-Stokes, which is
Yes.
very, very complicated. And then you applied the asymptotic analysis, assuming high Reynolds number and small amplitude of the fundamental mode perturbation. Yeah. Okay. And at this stage, yeah, so maybe these are the equations. It's complicated, but probably it's easier to solve compared with PSE or Navier-Stokes.
That's right.
Okay.
Yeah, this is solved at a particular location. Yeah, so we for these equations, the parallel flow is adaptation is valid here.
Mm-hmm. Yeah, so okay, so you don't have to merge your equation.
So for these equations, the non-parallelism are of high order impact.
Okay.
Yeah.
I see.
Yeah, we can evaluate them. So because the non-parallelism is about real number to minus a half. The leading order terms are much larger than them.
I see. And this asymptotic equations has some very special structure.
Yeah.
As shown in the next slide.
Yeah. Yes.
Sorry, previous slide.
This one.
Yeah. Sorry. Where you had some linear operator. I guess
this one.
Yeah. This one. So basically, if we simplify this picture as much as possible, you will arrive at this. I mean, the model, which is
Yeah. So for this structure, I just want to show the principal idea, because actually this slide is equivalent to these equations. That is just a skeleton of these equations.
And the same structure will appear in the simplified model. you showed later.
Yeah, yes. That's what I want to emphasize here. Yeah.
Mm.
Yeah,
Yeah.
and we can see some numerical results quite similar.
Mhm. Mhm.
So for example, here, so we can see this is the saturation state, just like the fundamental, this is the fundamental mode, the red one, and the blue one is the mean flow distortion, which is just driven by the fundamental mode. And at this stage, we can see the exponential growth of the streak mode and the oblique modes.
Mhm.
Yeah.
Yeah. So and interestingly, this model is a kind of a subset of a famous WRF, self-sustaining model
Yeah.
for subcritical transition.
Yeah.
I see. Mhm.
Yeah.
Yeah. So WRF, transition model is developed for purely subcritical problem where there's no
Yes.
linear instability. So for I can't remember, but for example, for I think WRF's model is somewhat similar to Lorentz model in field
Yes,
orbital point.
yeah. In principle, they are the same, but you have different elements.
Yeah. And I remember that the Lorentz model can be derived by Navier-Stokes equation by first applying Galerkin and truncate it very severely.
Yeah,
Can you do something similar for your model? For example, first you take.
At the moment, I haven't done this, but I believe it can be done.
Okay.
Yeah.
Yeah,
Maybe
interesting.
I can
Hi,
ask
Iman.
some related question. If you go to slide 18,
18. Yeah.
it was very interesting talk, a little bit outside my topic, but I was like curious to know this triad interaction, this resonance you talked about. Is it, first of all, is it valid at this transition region where the Reynolds number is below 150, or is it also the important mechanism when the flow is fully turbulent at high Reynolds number?
Yeah, actually, yeah. So the transition can appear at different Reynolds numbers. Yeah. So if and also it will depend on the initial perturbations. For example, in this picture, if the real number is this 70, like here, is 70, there could be a transition, a subcritical transition, a direct transition without the attendance of the instability modes. And if the initial perturbations are small, it will become go back to laminar. But if real number is a bit higher, we can see two different transition routes. The subcritical transition, which is caused by relatively larger initial perturbations, and for the for relatively small initial perturbations, we can see the supercritical transition, which is caused by the fundamental resonance scenario.
I have one.
Sorry, if I may add another question relates to that one. Now, if you see it in terms of flow control or drag reduction aspects, so is there a way, or what's your comment on manipulating this interaction? Is it possible, I don't know, from a tailored experimental setup or numerical setup to manipulate this interaction to achieve some, let's say, a delayed transition or to improve drug reduction capabilities?
Yeah, this model is just a skeleton. I think if you want to do some control, for example, the laminar flow control, you can do some DNS or NPSE. That's the one I showed before. From this model, I think maybe you can see some potential strategy for flow control, but it will not give you a quantitative result.
The asymptotic model would be.
Yeah, this is just a kind of a toy.
but it highlights this triadic resonance and interaction, and there is a large number of papers lately where they impose some kind of forcing at the wall, span-wise oscillations, other kind of where they target some. So I was curious to know whether this also related to that kind of work.
Yeah, that might be possible if you can introduce some inhomogeneous forcing from these equations, and the forcing, if the forcing can be related to some physical control strategy, then that could be possible to give us some information. And eventually, if we want to confirm this, we have to do some DNS work or something. But this can give us some valuable information, I think. Yeah, thank you.
Yeah, so you in your asymptotic model, the Reynolds number has been scaled out. So
yeah,
why do you
this part,
yeah? So why did you introduce Reynolds number in your model?
You see, we have a double layer structure. So in the main layer, the Reynolds number is scaled out, but in the wall layer, we have a thickness epsilon, which is just this one. Reynolds number appear here as a viscosity correction to the main layer.
Okay. So
actually, yeah, this number will affect, I think, let me see. Oh, this one. Yeah, epsilon.
Yeah, so it's a function of epsilon, not a
function
of Reynolds number. Okay.
Yeah.
Maybe in a model, for the simplified model, Reynolds number may be more related to this epsilon parameter.
Actually, this model is only for the fundamental resonance process within the laminar stage.
Yeah.
Well,
in your model, the Reynolds number was very, very small, whereas in your first calculation, Reynolds.
Oh, this one. You want this? Oh, yeah. Actually, this can be renormalized. Yeah, it depends on your reference lines. I can change it. Yeah.
Okay.
Yeah, it's easy to be changed. It depends on your reference lines. Yeah. So this real number is not the same as before. This is just in a toy model. We have not defined the reference lines very carefully.
Yeah. So any other question from audience? Yeah, there's one comment in the chat box.
Yeah. Is this in K? I don't know what do you mean K?
I believe they're referring to the wall temperature that you had in the beginning when you mentioned the wall temperature. Perhaps this AMNO is online.
This one? No, 18.
Oh, Kelvin.
I think it was here, yes.
This one?
Next slide.
Next slide. Yeah, this one. In K.
I think the question is about the wall temperature, like the unit of wall temperature.
Yeah.
Is it non-dimensionless, the values here, or?
Sorry, which one? Can you repeat it?
Yeah, for the temperature perturbation, is this?
This is the dimensionless. Yeah.
Dimensionless.
Which means let me see. About 7 times of the free stream temperature. So for this case, if the free stream temperature is 300 K, so sorry, I should say this is dimensionless temperature. So if the free stream temperature is 300 K, then this should be 2100 K. Yeah.
Mhm. So is this parameter choice typical for some application problem?
Yes, yes. It's typical.
Okay.
Yeah, okay. So you are not very familiar with the hypersonic flows. Yeah.
Yeah.
Yeah. So because usually we have a very high speed flow here, and it will eventually go. The speed will become 0 at the wall. Then much kinetic energy is transferred to the heat energy, and we will have very high temperature at the wall.
Mhm.
So that's why the temperature here will be seven times of here, of temperature here.
Yeah, I guess it's typical for hypersonic flight.
Yes.
Everybody concerns the Mach number around 6. Yeah.
Yeah.
Any other questions? If not, I guess yeah, we can thank again for the speaker. So very nice talk. Thank you, Ming.
Oh, thank you. Thank you for listening.
Yeah.